Decision trees. These I mentioned before. These are a lot of fun because they're very easy to understand. So we're going to use a classic machine learning data set about irises here. So let me do this nonsense here. Maybe we'll make a new notebook. I might be faster than logging in and logging out all the time. All right. So I'm going to import the iris data. All right. It's just determined to irritate me one way or another. See if it's going to do it now. There we go. All right. So this is a very simple problem. It's from a long time ago. I think somebody grew a bunch of irises and then measured different parameters of the iris. And there are three species of irises. He made 50 examples of each, and he measured various properties of them. And the goal is to predict what species an iris is from these measurements of the width and length of two parts of the iris. So here is the decision tree that does that. And this is very nice because it's so easy to understand. So what we do, we feed in the images, then we do a export the graph of this thing showing it, and here is the decision tree that does it. So the things we have are petal length and petal width. Those are the two parameters. And so each one of these boxes is just an if statement. If the petal length is less than or equal to 2.45, you go this way. Otherwise, you go that way. Then if the petal width is less than 1.75 or equal, you go this way. Otherwise, you go that way. That's all. They're just a diagram of if statements. Now, to measure the quality of your model, you use these things. Here's what's happening. Here I have the original data. All the data is here, 50 of these, 50 of those, and 50 of those, the three categories. So this is not sorted at all. There's a thing called Gini disorder, which is like entropy. It's a high number because you've got a mixture of many different categories here, so this is not sorted. What you do is you adjust this threshold to achieve the most efficiency in sorting the data. And see here, now it's 50 of one species and 0 of the others. It's perfectly sorted, so the Gini coefficient is now 0. So this is perfectly sorted. Just one measurement is enough to get one species completely separated. And now the only thing is to separate the remaining 50 to 50. So you pick the best petal width parameter to do that, and now you get imperfect sorting. 49 of one species, but 5 of the wrong species. And here you get 45 of the right, but 1 of the wrong. So the Gini coefficient is smaller, but it's not down to 0. But it only took a depth of 2 to accomplish that, 2 if statements. And like I say, it's very easy to understand what your model is doing. So if you don't like it, you could very easily figure out how to modify it to make it quit doing the bad thing. And so you can pull out the predictions, and this is pretty nice. You have width. So the first if statement was this way. It got this one complete. The next if statement is there. It did a pretty good job separating them. Now you can control the depth, which is how many if statements it's allowed to go. There is a depth parameter up here someplace. There, max depth equal 2. If I change that to 3, then I will fit up to 3 depth. And there you see, now I don't stop here. I then split these up more and get my Gini coefficient down even smaller. So instead of having 49 and 5 wrong, I have 47 and 1 wrong. Then I have one mesh here, 0, 2, and 4. Looks like my thing just died. Probably the battery just died or something. Yep, looks like it. Right, there's always something. Anyway, so you can see, you play with the depth. These things are easy to understand. That's the virtue of them. Let me go to here. All right. And now you can fit other kinds of data with decision trees. You can do curve fits. See if you can get another battery or something. Yep, thank you. Anyway, so here we're going to do, we're going to try fitting a curve with a decision tree, which would seem crazy, but in fact it works pretty well, as we're going to see. So now I got a scatter plot following a complicated curve here. That's my data. And so you do regression. Regression is curve fitting. And here we're letting the depth go to 2. So it's only going to make 2 layers of if statements. So it's going to be a pretty bad fit, as you can imagine. There. It's doing a really, really rough approximation of that curve with just 2 layers of if statements, which is what you might expect. But if you make the depth higher, it gets better. And if you don't limit the depth at all, which I think means you just get rid of the max depth, which is here. That's the plot. There's my depth. I think if you remove it, it's unlimited, or maybe you have to put in 0. I don't remember. Yep, that's it, because it's, here it is drawing it. It's got quite a few layers. And it doesn't go forever, because remember, at some point, it can't improve it. So if the Gini coefficient doesn't go down, it doesn't, so it'll eventually stop all by itself at some depth. And now your predictions will start to look like this. And you're just spiking every data point with an if statement. So in principle, you could overfit to a ridiculous extent, but you can do a lot with these things. Now that might seem extremely stupid, but it's less stupid than you might think, because you can make random forests, which is a real powerful machine learning model that you use. What you do is you don't use one decision tree, you make hundreds of them randomly and then combine the outputs. And the end result is you get a much better fit. So again, here's a data set. We're going to use one of these ones made of dots. I'll just try making a new notebook and see if that is faster. All right, maybe. All right, so there we are. We have a curved region of blue dots and green dots, and we're trying to tell them apart, and it's pretty noisy, so it's a bit of a task to do. Now we're going to classify it with an ensemble. What we're going to do here is have logistic regression, a support vector machine, and a random forest, and we're going to combine all 3 of them to predict the output. This is what you take different machine learning models trained in different ways and combine them, hoping that the errors will cancel out. So here, if you do that, you'll see the individual models have 86% right, 89% right, 89% right, and combining the 3, you get 91% right. But this is combining them in a really stupid way. They each vote on what category it's in, and you take 2 out of 3. The one who wins the election wins. Now that is one way to combine data from multiple sources and get an improvement, but it's not very smart, because the outputs are not just binary outputs, they're gradual outputs. You could probably do better than just combining by a voting system. And what you do is you do soft voting. In soft voting, each one of them has a probability of being right, and you average those probabilities. So you retain more of the information that the models extracted from the data. And if you do that, you go up from 91% to 92% accuracy, so it's somewhat better. Now you can do bagging. This is where you make many random samples from the same data set, and you train it on different random samples, just trying to get models that are different, so they'll have hopefully independent errors. And you'll see your decision tree makes this craziness all by itself. It's overfit, so it's made weird boundaries to try to, oh, there, finally this thing's working, okay. So you've made, this is overfitting, right? Instead of getting the actual trend, is that going to work? No, it looks like something weird is happening. Something.
There's no pass-through.
I think, oh, well, now something's working. All right, our technology is baffling here. Anyway, this is overfitting. It has made a complicated boundary, even a disconnected group of reds here, to more accurately fit the data, but it's fitting the noise, not the trend. But if you do this multiple tree and average them together, you accomplish the goal that these overfitting problems average out and you get a more reasonable boundary. So that's what people really use, and this is considered one of the most powerful machine learning models now, is these forests containing many decision trees averaged together. Even random decision trees where you don't even bother to optimize the border, but just randomly sort it by one parameter, the other parameter, you combine a bunch of those together. Now, there's other ways to combine multiple machine learning models to improve it. One is called AdaBoost, where you fit the data and then you increase the weight of the ones that you missed to get a correction term to fit the missing part and improve it step by step. That's one technique, and as you can see, you can watch it go. Now the problem, one important issue is the learning rate. If you're trying to do gradient descent, you're taking steps. If your step is too big, you'll jump past the minimum over to the other side and then past it again and just diverge, and that's what happens here. The learning rate is too high. You started with 1, then you went to 2, then you went to 3, 4, and 5. The learning rate is too high, so you don't converge to the bottom. If you slow down the learning rate, then of course you get a little bit better until you end up at the bottom. And that's an example of that. There's various ways to combine many of these decision trees together to make a better model. Let me stop this one.